the distance between the center of this detector and the center of that detector. As the pixel pitch decreases, meaning the distance decreases, it indicates that there is a large number of pixels present. So, if I now enlarge my pixel size in this way, from here to there, if there is a certain distance and a specific space, as the pixels start to shrink, this distance will decrease. When this distance decreases, you should have increased your resolution. Therefore, resolution is closely related to pixel density and the number of pixels present. As the number of pixels increases, the distance between the center of one pixel and the center of the neighboring pixel will decrease. Consequently, your sampling frequency will increase, allowing you to achieve a significantly better result. Here, increasing the pixel density and decreasing the pixel pitch, along with increasing the spatial resolution, decreases the pixel density and increases the pixel pitch, which decreases the spatial resolution. We talked about the necrotic criteria with necrotic frequency, and this example is exactly the same topic with no difference, but as I mentioned, I expressed it with this sine wave or my wave. As we mentioned, there is a specific condition that must be double compared to the highest one I have available so that nothing goes wrong. Just like you see here, if you have a specific condition here. Your pixels are able to see and sample this wave because it is low frequency. So there is no problem when the frequency of the object increases, meaning the number of offline pairs per millimeter increases. The same idea applies. There is no data missed, and you have created the aliasing present in the image. You can only see points here, 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 and here, but the rest of the signals or these parts, you cannot see them, so aliasing occurs, committing the same issue. Pixel pitch is the distance from center to center, and the sampling pitch refers to the sampling frequency. I've noticed that this term can be a bit confusing in the context of sampling frequency in the questions. What is meant by sampling pitch is actually the sampling frequency. So pixel pitch is the distance from center to center. To be more precise and comprehensive with the information here, I have a matter. Let's assume that I am changing the signal frequency, which is my object in this particular context. I am either decreasing it or increasing it, or whatever I am doing with it, or perhaps modifying it in some way. The blue color increases the frequency, and here we notice that the frequency was low, so I increased it. The red line, which represents the red points, is the sampling frequency. Now let's see the relationship. If I have, for example, the signal or the frequency of the line pairs at 25 Hertz and the sampling frequency is 50 Hertz. Sorry, here the signal frequency is 6.9 and the sampling frequency is 22, which means that the sampling frequency is higher than the Nyquist frequency of 6.9, more than double. This means there will be no aliasing. But what if we reduce the sampling frequency? Aliasing artifacts have started to appear. If we increase the frequency of the line pair and keep the sampling low, you will find that aliasing frequency occurs. To prevent this, you need to increase the sampling frequency. The more you increase the sampling frequency, the more you will see the value of aliasing decreasing until it changes. The minimum sampling frequency that does not produce aliasing artifacts should be double the Nyquist frequency or the maximum frequency present in your object or in the image you are capturing. Is this clear? This is a thought. The sound dock is no longer coming from the speaker. Oh, I'm sorry for the inconvenience. What is the place? What is the place? It must be, yes, it must be double or more. Look, doctor, remember the question about the fill factor that you asked me? You told me that if the pixel size decreases, meaning the number of pixels increases, then what happens to the resolution? The resolution will increase. This is what we are discussing today. It's the same story, but at whose expense? Remember the topic of the sensitive area decreasing? You need to increase the dose you give to the patient to compensate for that sensitivity. This is one story, and this is another. The topic of sensitivity and resolution always works against each other. If you want resolution, you need to improve your detector to accommodate a larger number of transmitted photos. That's great, but at whose expense is the resolution? Their relationship is always inverse. The topic of resolution and sensitivity is like using a thin screen or a thick screen. The thin screen gives you resolution but reduces sensitivity. Why? Because the same idea applies. Light undergoes diffusion over larger distances, so when you try to do detection, you are not following its path correctly, leading to a higher probability of detection occurring here or there, which starts to cause blurring or reduces the resolution. The same idea applies to sensitivity and resolution. These are examples of aliasing artifacts that appear, such as lines in the image, resulting from the existing aliasing artifact. For instance, when you use CT image reconstruction, you might use a pixel size, and in some examinations like the Petra's poem, you need to increase the resolution within it. It tells you to increase the standard matrix size for CT. For a regular image, it might be 512, meaning 512 by 512. For CT, for example, 512 by 512 by 512. 512 rows by 512 columns. Okay? So when you talk about something that needs, for example, they tell you to increase the matrix to 1024. If you didn't increase it, you would find that you see these lines or these stripes present in the image. Why? Because there is data here, missing data that should have been here as an object, giving you a signal. You lost this signal. You didn't store it. You didn't digitize it. And there are no pixels that you could see. So you find that the point or the lines that appeared are as if they are an average signal coming from two objects next to each other. So it stored it here with different intensity, with a different city number than its actual city number, and thus the shapes or the shape appears aligned in this way, and this represents an aliasing artifact. Similarly, for example, in ultrasound or in MRI, when we talk later about aliasing artifacts, here, I am explaining everything I was talking about regarding matrix size and pixel in this part. Here you will find, as I mentioned, that there is a strong relationship between imaging modality and spatial resolution. For example, you will find the CT at 0.7 line pairs per mm. That's why, for instance, in the specifications, the topic of spatial resolution is very important for you to see how many line pairs per mm you can observe. You even conduct a test for it, which is evaluated using something called the cat fan phantom, or some existing phantoms, and you start to see the line pairs, as we mentioned earlier, how many there are. Perhaps I explained this to you before when we were discussing the MTF. Is the MTF concept clear, or should I explain it quickly? We will talk about resolution. Thank you. Of course, it's 1 out of 0, 1, but we represent it in percentage, Dr. Rian. So we say 100% is like 100%, right? It's 1. 0. You don't have an image. No data reached you. 1 is the highest. The image that came out to you is the same as reality. It's the same as the real object. That's the highest. Providing information about the actual image means understanding its intent, which is to show the resulting image and the object itself, along with its contrast. Logically, it raises the question of how one can claim to improve it by 100%. This improvement could refer to enhancing the contrast or resolution of the image, which is a different matter that can be addressed through post-processing. But how can one claim to achieve 100% improvement? It is 100% the highest value. If you have a need, doctor, or if any of you have read it somewhere or it's not understood or something like that, you can send it to me and we can discuss it. Because sometimes the context of the conversation itself can lead to misunderstandings, for example, and it happens in an epidemic way. Okay? No, excuse me. Okay. As we said, the value of the explosive needs to be calculated. And to do that, you have to use something called the line spread function. The line spread function is then input into something called the Fourier transformation, which gives me the value of the explosive. This is a big topic with more details, but it relates to what I was explaining last time to Dr. Hani. I told him that I have a line birth. I take a line, and this line gives me something called a line profile. Okay, this is the frequency, and this frequency before the Fourier transformation is transformed into the curve of the explosive like this. We were talking about this topic. The calculation or the calculation process, how is it done in detail? I said I have a phantom object. This phantom object contains a group of sets of lines, specifically with varying numbers per millimeter. I have a group of 10 lines per millimeter, a group of 20, and a group of 30. Okay, each group takes a region of interest, ROI, and calculates the standard deviation. The standard deviation expresses the extent of variation present, meaning the imaging system itself can see a difference between the line pairs and the sample. If it sees all the line pairs as one entity, without differentiation, it will perceive them all as the same. So, when I take the ROI, I find that my standard deviation is very low. For example, if you have something in the city, and you want to slice it, but this thing is next to something else, every time you take your ROI, you find the value of the Hounsfield unit blending into the value next to it. The same idea applies here. All these gaps are not visible, so it sees everything as one. Therefore, the standard deviation here is low. because it reflects the amount of variation present in your image. The value of the standard deviation here represents the extent of the resolution present. The greater its value, the more variation the imaging system can detect between the line pairs. In this case, your resolution will increase. So, what do? There are two methods. One is visual assessment, for example, asking if I can see this group with my eyes. Can you see this group? Yes. 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 Are you saying that the machines is done? But why the topic of the explosive? The explosive has values, right? These values range from 0 to 1, where 1 is the highest, meaning 100%. What does 100% mean? It means that your object is seen in reality. Your system or imaging system sees the 30 line pairs per M just as they are in reality, just as they appear in your captured image. So the efficiency here is 100%. Now the standard value of MTF can be 10% at a value of 0.1, which starts to show how many line pairs per M your imaging system can see. So you are saying what the MTF is at 10%. Your imaging system was able to see how many line pairs per millimeter. Consider what you are saying about the MTF. When you say how many line pairs per mm, it's like saying that your modulation transfer function, which reaches 10%, allows you to see how many lines are present. It doesn't have a unit, but as I mentioned, it represents the resolution of your machine. This efficiency indicates the level of performance of your machine. When it reaches 100%, that's the highest efficiency for your machine or your imaging modality. Now at 10%, that's the value you use as a standard to evaluate one machine against another, not at 100%. You evaluate at 10%, right, doctor? All right, let's get to the important topic here, noise. I received some questions like whether noise increases with the number of photons or decreases with the number of photons. This question, and whether it increases with the standard deviation or decreases with the standard deviation. I'm sure you all have seen in the questions about this noise topic. Does noise increase if the standard deviation value increases? Does noise increase or decrease? And if I increase the intensity of radiation and the number of photons increases, does noise decrease or increase? Does anyone have any inquiries about this noise topic? Let's discuss. What does standard deviation mean? Okay, fine. So I asked a question and you took me to another point. All right, now there is something called statistics, which is a branch of mathematics dealing with data collection, analysis, interpretation, and presentation. Standard deviation is a measure of the amount of variation or dispersion in a set of values. In statistics, a low standard deviation indicates that the values tend to be close to the mean of the set, while a high standard deviation indicates that the values are spread out over a wider range. This concept is crucial in fields such as finance, research, and quality control, where understanding variability is important. If, for example, I entered a place where everyone there has a height of 150 centimeters, then I have in this place about 30 people, all of whom share this exact height measurement, making it a unique scenario. All the people have a height of 150 centimeters. So is there any variation in the height of these people? There is no variation at all. Great. When I tell you that the mean value of the heights of the people present is 150, there is no change. So my mean is the same as your value, and the standard deviation, which expresses the amount of variation, means that if I were to draw a curve, representing the number of persons present and their height, I would find that all the people, not a curve, not at this time, just add the number. All people will have one value. For example, let's assume the value here is 150. So all the people present should have the same value, which is 150. If I were to number the people present, there is a curve called the Gaussian curve, or Gaussian distribution. The Gaussian distribution represents the average value, which is the mean or average of the heights of the people present, and the amount of variation from this average value, which is the mean value in the data set. The variation from the mean is denoted by the symbol, the Greek letter sigma, which is the statistical measure, known as the standard deviation, and it equals the square root of the average value in a data set. Thus, the standard deviation expresses how far I am from the mean or average value in the data. The more this variation increases, the more your graphical representation or curve will look like this. The larger the standard deviation, the more values you have that are further away from your average. So, the standard deviation here gives you information about the amounts of variation or the distance from your average value. When you come to the CT, computed tomography device, and say you want to take a specific region of interest, the mean appears, which is considered the house field unit that you take, and you will see the maximum value and the minimum value. The maximum value is simply a pixel that represents the highest pixel value in the image or intensity in the data set or collection of interest. The minimum value is the lowest pixel value in the analysis or study. The mean is the average, which is the sum of all these pixel values divided by the number of pixels present in your region of interest or area being examined or evaluated. The standard deviation is the square root of the variance, which indicates the amount of change or variation in the context of this examination or assessment. If there is a significant difference in pixel values, the standard deviation will increase. Logically, this means that your noise will also increase. And indeed, this is what happens. This is known as quantum noise in the field of image processing or analysis, in the domain of digital imaging or photography. What is quantum noise? Statistically, what I just said is completely fine. No problem at all, right? Quantum noise is the square root of the number of photons. Is that correct? So, there is direct proportionality when the number of photons increases, right? Your number of photons increases. Based on what I'm saying now, quantum noise should increase. But this doesn't actually happen in reality. When the number of photons increases, the signal increases and the noise decreases in the image, making the image better, right? So why is that? Because the noise mentioned in the question is not quantum noise. It is something called relative noise. What is relative noise? It is the relationship between standard deviation and the number of photons, as if you are saying that the noise present has a certain ratio to the number of photons within the region of interest. Therefore, there is an inverse relationship between the number of photons and the relative noise present. What is the ratio? It is the relationship between them and the photons present inside. There remains an inverse relationship between when the number of photons significantly increases, the noise substantially decreases. And when the standard deviation essentially increases, the relative noise increases. This is what is often asked in questions or discussed. I cannot treat noise as an absolute value. It must be considered relative to the existing signal. Now, if we say the average number of photons coming to the detector here is 1000, and here is 100, the quantum noise here is the square root of 1000, which is 31.6. And for 100, it is 10. How is that? The number of photons is significant because you are dealing with statistics here. You are not concerned with anything else. You are talking about quantum noise, which is related to the distribution I mentioned earlier. So, when you divide this noise by the number of photons present, what you get is sigma, which is the relative noise. How much will it come out to? 3%? 10 over 100? How much does that come out to? 10%. So, what happened with relative noise? With 1000, it's 3%, and with 100, it's 10%. This is logical. This is what I see in my image because you see relative noise, not quantum noise. You see the noise to signal ratio that exists. Okay? This is what you see. So the relationship between the number of photons and noise is an inverse relationship, right? Is there a question about this part?